Okay, question 4 says, what is the centripetal acceleration of the car? And so the first thing you're going to realize is, okay, my centripetal acceleration is a plug and chug formula, v squared over r. And you certainly have the radius of the track, but you are not given the velocity. So you want to use logic to figure that out, that you know the time it takes to make one complete a lap of the track, and we want to find the speed, and the speed is distance over time, and the distance it travels in one rotation is the circumference, or 2 pi r. Okay, so to find the speed, you're going to take 2 times pi times 2,600 meters. Always make sure it's the radius, not the diameter, and vice versa. Just be careful because that trips me up sometimes. Over 360 seconds. And then that yields a speed of 45.4 meters per second. And now we're ready to just take that information and plug it into the centripetal acceleration is 45.4 meters per second squared over the radius, which is 2,600 meters. And you get 0.792 meters per second squared. And that should make sense, right? Because remember, 1g is 9.8. So that's 1/10 of a g, which makes sense when you're not being flung to the side of the car with a lot of force. All right, so the tricky part there was figuring out the velocity. Hope that one made sense. All right, question 6 is about the astronauts training to survive G-forces. And what you're given is that the astronaut is subjected to 7.5 Gs. So what that means is their centripetal acceleration is 7.5 Gs, which is 7.5 times 9.8, or 73.5 meters per second squared. Okay, so that's one piece of information, is understanding what a G represents. And then the second part, again, is the plug and chug into the formula that the centripetal acceleration that the astronaut feels is equal to v squared over r. And we have r, and we're looking for v, and we calculated what a needed to be. So a is 73.5. That is going to equal our unknown squared over the radius, which is 15. That gives you v squared is 15 times 73.5. I'll cross multiply, or multiply both sides by 15, however you want to think about that. And oops, that means v is the square root of that. And so you get 33.2 meters per second, which is about 60, 70 miles an hour. Okay, awesome. Hopefully that makes sense. Okay, you have a salad spinner question, and this is a great example of the fake centrifugal forces. It looks like the lettuce is stuck to the walls, but it's really, from a bird's eye view, the lettuce is trying to fly off tangent, and it runs into the wall. The water on the lettuce is trying to fly off tangent, and since the water can fit through the holes, the water will fly off tangent, leaving the dry lettuce behind. Okay, so that is what's going on. Question A says, what is the linear speed of the lettuce? And you might say, linear speed is 0. It's not going in a line. It's going in a circle. What they really should say is the tangential speed, meaning if the wall suddenly broke, boom, with what speed would that lettuce fly off tangent? So again, that's just thinking about like the first one problem on this problem set. The speed, if that lettuce had an odometer on it, it's the distance it traveled divided by the time. So 2 pi r is the circumference. It travels this much distance every rotation. And this is a little bit tricky. It does 2 revolutions per second. So it's a little bit easier if we're dividing by the time. That kind of makes sense. But you can think about this as, okay, well, the time I have is 1 second, which means it doesn't do 1 circumference in that time. It does 2 of those. So you're going to take the circumference and you're going to double that because that is the distance it travels in 1 second. Okay, and then you're going to multiply the numerators and then divide by 1. So you get that lettuce is clocking it at 1.501 meters per second. That is the answer to A. And then B, the centripetal acceleration is plug and chug into V squared over R. And so you take your 1.51 meters per second squared and you divide by the radius, which is 0.12 meters. And you get that is 19. So almost, the lettuce is feeling almost 2 G's, which is pretty strong. I don't know if that's a realistic problem or not. Okay, that was the end of centripetal acceleration, and getting practice with thinking about how you calculate velocity for going in a circle. See you in class.